Hello, everyone. So today we're going to hear a talk from Dr. Soham Chakraborty. So Soham is a postdoctoral researcher at TRIUMF in Canada. He received his MSc in physics from the University of Calcutta in India before continuing on to study a PhD at the University of York in the UK. So after finishing at York, he joined the IRIS group at TRIUMF. IRIS stands for the ISAC Charged Particle Reaction Spectroscopy Station. His research interests include both direct and indirect measurements of nuclear reactions, which are important for understanding the nucleosynthesis in different cosmic environments, and probing the nuclear structure of rare isotopes. He's also directly involved in the development of TACTIC, which is an active target time projection chamber designed for direct measurements of alpha-induced charged particle reactions. And we're going to be hearing a little more about that today. So Soham, whenever you're ready, take it away.
Cheers. Thanks, Cameron. And hi, everyone. Many thanks for joining today's seminar. So like Cameron mentioned already, today I'm going to mainly focus on TACTIC. So TACTIC is a detector that was developed to study basically nuclear reactions with astrophysical significance. The development and commissioning of TACTIC constituted a major part of my PhD thesis. And like to start off with, this is one of my favorite pictures from JWST. You can see this is like a mid-infrared instrument image of Cassiopeia-A supernova remnant. And you can see like, different colors. It's like the X-rays are color shifted. Infrared is color shifted. And basically you can see the different materials being ejected out into the ISM, the interstellar medium, and which is like a cool visualization for like nuclear astrophysicists, because like this is like an active site where you can just clearly see that like nuclear elements that were synthesized inside the stars getting pushed out. So yeah, I think that this motivates TACTIC quite nicely. So with that, I'll just introduce TACTIC. So TACTIC is the acronym for TRIUMF Annular Chamber for Tracking and Identification of Charged Particles. Yes, it's a long one. And the development of TACTIC actually commenced in 2007, so which is like well before my time. So it has been on the pipeline for a while now. But I'm glad that I'll be finally able to share some nice results with you today from our recent TACTIC tests. So what is TACTIC? It's an active target TPC, a time prediction chamber, and it has a cylindrical geometry. You can see a cross-section of TACTIC on the top right-hand side of this slide. I'll definitely talk about active targets and time prediction chambers more in detail, just so you can grasp the keywords. What we try to do, the development of TACTIC currently focuses on the direct measurement of charged particle-induced nuclear reactions. Basically, I'll also motivate that in the future slides, just so like you have a good idea. So the sites of interest are like, as it's very evident, I love this picture of Cassiopeia-A. So this is clearly a site of interest. It's a core collapse supernova. And then we also look at different nuclear reactions that drives nucleosynthesis in sites like type 1A supernova, massive stars, and also accreting neutron stars. So yeah, some more scientific motivation. So the explosive nucleosynthesis, the phenomena the cosmological sites like this basically play a key role in enriching the ISM interstellar medium. So during the lifetime of the star, it produces different elements through nuclear fusion reactions. And then once at the end of the lifetime of the star, it explodes violently, causing the core collapse. And then the shock wave basically takes all the materials and basically ejects that into the interstellar medium. So yeah, and these are important because you can clearly see there are direct evidences from gamma ray decays of different isotopes like 44 titanium and 56 nickel, especially from core collapse supernova scenarios, basically. So you can observe them from ground-based and also space-based telescopes. So yes, these allows us to understand the workings of the stars, which are basically factories that produce all the physical elements that we see around us today. So yes, so from those observations, there can be sensitivity studies can be done. So there are hundreds and thousands, even nuclear reactions that are taking place simultaneously at different stages of a star's life, basically. So in order to understand like which reactions are important for us to study to highlight the key properties of the star, there can be sensitivity studies. So basically, you can see in this, like in these nice plots, it's from one of the sensitivity studies, a theoretical study that was done by Subedi et al. And it basically on the horizontal axis, you can see the reaction number. Well, it's not, reactions are not evident, but then again, these charts like 50 different reactions, and then how they impact the titanium to nickel ratio. So titanium and nickel are quite important in core collapse situations. So, and you can see that like from the baseline, if like the sensitivity study is in the studies, you change the rates of certain reactions that is highlighted in the x-axis, then you get like a under or overproduction of like 44 titanium and nickel. So it's very important for us following these studies as experimentalists to understand, to try to devise experiments to understand and constrain the reaction rates for the key reactions that are pointed out. So by the studies. So 17 fluorine as an example, alpha P, antimony 7 aluminium alpha P. So these causes like the first two spikes in these plots. So yeah, it's quite important. And there are many ways that you can study these reactions. So there can be, grossly speaking, there can be a direct measurement approach and there can be an indirect measurement approach. So I will be focusing on the direct measurements. So basically, direct measurements, what do we measure? We measure compound nuclear reactions. So that is basically the fusion of the projectile and the target nuclei. So what happens is in this nice cartoon, you can see that there is a projectile that's hitting heavy nuclei, and then you form an intermediate compound nucleus, and then it can decay with different channels with certain probability. So what happens is in the lab situation, in the lab frame, the target nuclei is fixed, is kind of static. We can assume it's static, and the energy of the projectile, after hitting the heavy target, it gets distributed. The energy gets distributed among the nucleons of the compound system, and then giving rise to the compound nuclei, and then downstream decay. So, what do we measure? Basically, we measure the reaction cross section. We can measure different things, but then again, I'm going to focus on the reaction cross section measurements. So that gives us the probability of the reaction taking place at a certain energy, and also the study of resonances can be done. I would also want to highlight the term inverse kinematics because, like in this cartoon, it's a light projectile hitting a heavy stationary nuclei. In tactic, we have a heavy projectile which is hitting light nuclei, but not light target nuclei. So this has certain advantages. So what it does is it allows us to study nuclear reactions involving short-lived exotic nuclei, because it is very difficult, if at all possible, to produce targets with short-lived nuclei. That's where like, you know, the research facilities such as TRIUMF and EFRIT come in. So they can produce, from the accelerator, they can produce different short-lived exotic nuclei beams. And we can have like targets, different targets like helium, hydrogen targets, either in gas form or in solid form, and we can have the nuclear reaction. We can study the nuclear reaction once we have the target and the projectile, basically. So it's quite important, the inverse kinematics, to push the boundaries of the reactions that we can study. So in a dark measurement, this is the very rudimentary formula that we use to study the cross section to calculate the cross section of a reaction. So it what we basically measure are like the quantities like yield. So you can see that once we know, so the NB is the beam energy, NT is the target density, and sigma is the cross section, and epsilon is here the efficiency of the detection efficiency. So basically, we have if we know the target density and the beam intensity, then we can measure and the detect from, if we know the detector efficiency as well, we can, if we know the yield from our measurements, we can basically calculate the cross section. So it's not always bright. It's mostly the reactions that we look at usually have quite low cross sections, especially at very low energies. So low cross-section measurements are quite challenging because you can see that once the cross-section is low, then like the yield of the reaction will be also low. So either there are ways to do it. So practically you can run, well, theoretically you can run forever, which is usually not the case due to like the competition and the feasibility of the experiments. You can just run forever. So what we can do is we can maximize the beam intensity and the detection efficiency of the detector facility in order to target these low cross-section measurements. So that's why we need high intensity exotic beams. That's where TRIUMF comes in, and also high efficiency detectors. That's where a tactic comes in. So I'm just gonna motivate like what are active target detectors and what are the key differences between conventional detectors. This will come in handy when I further talk about tactic, which is an active target detector. So active target detectors in principle are basically, there's no physical separation between a target and the detection volume, meaning that in a detector like TUDA or IRIS, so these are basically silicon detector arrays. So what you can either have a solid target like in IRIS, or you can have like a solid or a gas cell. So after the reaction takes place inside the target volume, that is gas or the solid target, the reaction, the particles coming out, the ejectile and the heavy and the light nuclei, they will lose energy in the target itself before escaping the target. Also, we have to take into consideration the dead layers, and we have to reconstruct the energies. So that can lead to certain uncertainties and loss of information. Especially, this becomes important when we go lower and lower in energy. Think convective shell burning. That's like really low energy physics. So active target detectors eliminate that physical separation. That is for gas cell, there's a window that separates the target from the detection volume. And for solid targets, the target itself causes the reaction products to lose some energy. So in active target detectors, there's no physical separation. That means the target gas is itself the detection volume. So you can see this nice cartoon of ACTAR, this nice diagram. So the incoming beam particle reacts with the gas, and then the detection gas basically gets ionized, and you collect ionization electrons. So there is no separation. So you can start the tracking or detecting your particles instantaneously right after the reaction. So you don't lose any information in the separation between the target and the detection volume in a conventional detector. So these active target detectors are usually gaseous detectors, and they are time projection chambers. So I'm going to talk about time projection chambers a little more. So for key components of a time projection chamber is the drift region. So drift region is basically after the reaction takes place, and you have the reaction products going out and ionizing the gas, a region that causes the electrons to drift towards so basically what happens after the ionization in the gas takes place, the electrons will drift towards the anodes from the cathode. So you have the drift field in the drift region, and then you have an amplification region that basically gives you an avalanche amplification, and that is especially true for like light ejectiles because they deposit small amounts of energy in the gas. So you amplify the original electron signal, and then you collect the signals in a segmented anode plane, which can be very fancy and very intricate. Depending on your requirements, you can do the segmentation in a way where you can see a shadow of the track like Actor does. They basically see a shadow of the track on their path plane, basically. And also then you have the readout electronics that constitutes, that gives you the signal that's constituted of the DAC and also the preamplifiers. So now the question is, why use active target detectors? Is it just the fact that you don't lose energy in the separation between target and detection volume? Then you can just argue that, well, you can just reconstruct it. But then again, there are other advantages to active target detectors as well. So main one is that you can study the entire excitation function with a single beam energy. So because this is a cross-section of tactic, so what happens is the beam comes in and the beam loses energy. And because you track the vertex of the beam of the reaction, basically, you can have as the beam loses energy, you can have like multiple points. You can have like at different energies, you can have reactions with the same beam energy. So the beam loses energy, and you can scan the entire excitation function with a single beam energy. It gives you a very time efficient measurement, which is like gold, especially for radioactive beams. Time is of essence, to say the least. Also, active targets give you thick targets that gives you more density, like in terms of like target thickness, that enables us to do the measure small reaction cross sections. If you think back at the formula, the target density impacts the yield. So yes, thick targets, more higher density, and then you can have like more yield. Also, the 3D reconstructions of the tracks are possible, and also because you can have the detector geometry in a way you can maximize your geometrical acceptance, increasing your detection efficiency. So a few examples of active target detectors. So music at Argonne, they have like a very highly efficient detector with detection efficiency close to 100%. They rely on segmented anode structure and energy loss of the beam itself. So they do really nice measurements. Also, Actar, I have like motivated before. So they have used also in addition to the gas detection, they use silicon detector arrays and also they do track particles, and they use micrometers for gas amplification. So this gas amplification stage is quite important for these active target detectors to detect a range of different ionization from different particles from light to heavy. Also ATTPC at EFRIB, which is a really nice magnetic field. Again, I haven't included the picture, but it's very interesting how they do it. They detect their light protons, and in order to completely stop protons, they use a magnetic field, and that gives the track a spiral shape, and which is very cool. And also they use a very dense readout channel and thick gem and micrometers. These are for gas amplifications. So one of the main limitations for these detectors are they're rate limited because the beam ionization overpowers the detector electronics. So you can only go up to a certain beam intensity, 10 to 5 particles per second, give or take. Otherwise, you tend to saturate the electronics and get piled up. So that's a limitation currently for most of these detectors. That's where tactic comes in. So the main USP of tactic is basically the central cathode cage, which traps the beam ionization allowing tactic to go to a high beam intensity. So we have tested tactic with a beam intensity up to 10 to the power 7 particles per second with negligible pileup effects. Also, other key features of tactic are like tactic uses entry and exit aluminized mylar, really thin aluminized mylar as entry and exit windows. Also, for the gas amplification, tactic uses micro-RWELL, which is the beating heart of tactic. I like to say that because tactic was, like I said, tactic development had started as early as 2007, and we tactic implemented different gas amplification methods. The previous ones didn't work too well. So, but then again, these micro-RWELL detectors have been a recent development, and these are very novel gaseous detectors. And I'll mention, this is the first time active target detector has implemented the micro-RWELL technology and inside a cylindrical geometry. So yes, it's one of the key components. So cathode gauge and micro-RWELL is by far like the most important components of tactic. Also, like we use custom-made charge-sensitive preamps. So tactic has 480 readout channels that are basically distributed into 8 sectors, and these sectors, including 60 pads, run parallelly to the cathode gauge. So the idea of tactic is the beam will come inside the cylindrical geometry, it will react with the gas inside, and then you have the reaction product ionizing the gas and with the same gas as the target gas. That's why it's an active target detector. And then you have the electrons, the ionization electrons moving towards the micro-RWELL. That's basically placed radially outwards. And then the amplification will take place inside the micro-RWELL, and you induce signal in the anode pads and detect, basically. So the micro-RWELL, like I said, that like is a very novel detector, and there wasn't a lot of like studies available, especially for the helium gas mixture of interest. So helium we need because for our alpha P reactions, that is the only target gas that we can use. So we needed to test the micro-RWELL in helium-based gas mixture to study the performance and what kind of like gas gain and energy resolution we can have, and also like what kind of like noise and like what's the low energy detection capability of the micro-RWELLs. So in order to do that, we put the micro-RWELLs in a test chamber inside tactic. So inside tactic. Test chamber is a separate installation, and basically it's a planar analog of tactic. So it's very easy to mount the detector, the micro-RWELL detector inside the planar geometry. So what we did is we obtained the micro-RWELLs and we tested them inside the test chamber, and we got the results out. And what we did is we benchmarked with argon gas, and we studied, as you can see, the gain is basically a multiplication factor. So when you see 10 to the 4, that means for 1 electron, you'll get, from avalanche, you'll get into a 4 number of electrons. It's as simple as that. It's just a conversion factor. So high gains are important when you are trying to detect low energy signals, which is trivial, but I had to say it. But so yes, the key takeaway from this plot is we saw consistent high gains across different gas mixtures, including helium gas mixture that we needed basically to study, because that's the target of interest in tactic. And also another nice result is, so this is an iron 55 spectrum. So iron 55 is an X-ray source, and it produces 5.9 keV X-rays, which gets converted inside the gas, and you release an electron, and that electron ionizes the gas. One thing I should make clear, that the test chamber and tactic, they are blind to gammas, X-rays, and neutrons. So they can only detect charged particle ionization. So yes, so what we could do is we could do in argon gas mixture, we saw this 5.9 keV and this really low 2.7 keV peak above noise. So that was a revelation. Like that gave us the understanding that, okay, now we are capable, we should be able to put tactic and expect similar results of low energy in terms of low energy detection, right? And that led us to install tactic in, the micro-RWELLs inside tactic. So that was done here at TRIUMF. So we obtained these large area micro-RWELLs. You can see like the pad surfaces, the anode pad connectors on the bottom side, and then like on the top side you have like the micro-RWELL surface, which looks like a flat surface, but it has like really small microscopic tiny holes in them for avalanche. So this installation inside tactic. So this is a nice clean room picture. Myself and Warren, a postdoc back then, helped me to do this work. It's like nice micro-RWELL. So we installed the micro-RWELL in cylindrical geometry. It looks quite nice. It's like a barrel. So this marked the first integration of micro-RWELLs inside cylindrical geometry, right? So we're really excited to test it out. So, and tests we did. So this is like a comparison between, on the left-hand plots, you can see that the simulation. On the right-hand plots, you can see the real data. So this is an alpha source comparison. So I should mention that a Geon4 based simulation was developed for tactic. It was done by Warren and Julian. So Warren was a postdoc and Julian is currently a research associate at University of York. They did a really nice job implementing this, using the NP-tool framework and implementing tactic into it. So what we did is as a first sanity check, we tried to test the detector with the alpha source and see how we agree with the data. And the simulation is basically shows you that radioactive source and alpha source is placed inside tactic, and you have the alpha rays coming out, ionizing the gas. The gas being helium CO2, which is our gas mixture of interest. So you can, what we saw like is like nice agreements in terms of different parameters, like track length, theta, that's the track angle, and also the multiplicity, number of paths fired in an event. So these are all important tactic parameters that I'll discuss. But then again, the main takeaway is the agreement was reasonable, and it was quite good. It followed the similar shapes and structures, and also the limits were recreated like quite nicely in the simulation. And you can see the one-to-one comparison with data. I try to keep the ranges similar so you can see the similarities in the shapes. So based on that, our successful alpha source tests, we requested a stable beam time from TRIUMF, and we're given sodium 23 and 14 nitrogen stable beam time during 2022 and 2024. Big thanks to Chris Rees for putting that in the schedule as a test or discretionary beam time. He was kind enough to trust tactic. So so what we performed is the direct measurements of 23 sodium alpha P and 14 nitrogen alpha P reactions. Why we chose 23 sodium alpha P reaction? First, it is an important reaction in the type 1a supernovae scenario, heat for producing the heavy elements basically in the chain. So also, as you can see in this like Hubbard et al. The plot, nice cross-section plot from Hubbard et al. This reaction has been studied multiple times in the past with different detectors, both active target and conventional detectors, and the data agree with the theoretical predictions, the Hauser-Feshbach predictions within 10 to 15%. So this is a nice data set that we can follow basically to find to do the first test of tactic, right? And this is tactic installed in one of the beam lines, the TRIUMF ISAC-I beam line, all ready to go. Yeah. So I just wanted to show this picture because I wanted to note that all the data I'm going to show actually came from an experiment and tactic was actually installed. So we didn't doctor the data. So yes, silicon, so a stable beam test at TRIUMF, like I mentioned, was done at back in 2022 and 2024 as well. So the 2022 data was analyzed by me, and it went to my thesis. And the 2024 data, we did the same test again. So the 2022 data was restricted in terms of the beam time that we can actually focus towards the actual measurement, because we are doing a lot of test changes and stuff like that. So, but 2024 data, we finished our run last October. We have a large, like a good chunk of data to get good statistics out of that. And also the 14 nitrogen data is currently being analyzed by one of the master student in the University of York. I would like to mention, and I'll come back to this in the next slide, that like tactic data interpretation relies on pulse shift analysis. So what we do, we record full waveforms, and I'll come back to that as well. And also the data analysis has two key goals. One is the vertex reconstruction that gives us the beam energy at the vertex, at the reaction vertex, and also the particle identification that gives us the reaction product of interest and the yield of interest, which translates into the vertical axis here. That's the reaction cross section. So there are many complicated aspects, but then again, I'm going to try to streamline as much as I can the analysis. So this is basically a waveform from the digitizer, a waveform plot, basically. So what you can take away from these plots is basically each horizontal red line here is one of the channels, one of the preamp or digitizer channels. And when you have like an event inside tactic, you can see ripples in the channels. So that tells you that we have an event. So that's how we identify events. And you can have different sorts of events. Like on the left-hand side, you can see this nice Bragg peak signature where the particle would start somewhere around here, right? Close to the window. And then it will lose energy inside the gas volume. And before it's stopping inside, it will like deposit the highest amount of energy. That's the Bragg peak signature, which is quite nice to see. And then you can probably this is a heavy ion, and then also some heavy ions will saturate. You can see the peaks are cut off, and then you can have like light particles which trigger a lot of pads, and you can see like a disturbance in like a large number of pads. And the Bragg peak signatures are not evident because the protons won't stop inside the gas volume. So you get like more averaged over energy deposition over a large number of pads. So yes, the vertex reconstruction is done from the trigger time, the rise time, the multiplicity. So these parameters come together to give us the vertex construction, and the pulse amplitude gives us the idea of the deposited energy. So that helps us to do the particle ID. So the first, like I said, the vertex reconstruction can be done inside tactic. So what we do is we track the particle inside the detection volume, and you can see a nice reconstruction of an alpha track inside tactic. So one of the key assumptions that we make inside tactic is that tracks are straight, and also they start at r is equal to 0. That's basically the center of tactic. The key parameters that we look at are trigger times of like for each pad, the track radius that we can calculate from trigger time, combining it with Garfield, and then track angle and track length, multiplicity, that's number of like pads fired, So you can, in this track, you can see that like the number of, like each pad fired is signified by the green dots, and then you have a fit, and you have the exfoliation into the cathode gauge to identify the reaction vortex. And that's basically the method how we identify the reaction vortex. And then you have the pad positions and the pulse amplitudes as well. So from the vertex construction, it was a sanity check with the alpha run and also the sodium-23 run. We saw that like the vertex the vertex position agreed well with the measured source position for the alpha run, and also for the sodium-23 run, the beam run. These two red vertical lines, they signify the limits where we expect they basically signify the first vertical line is where the beam enters, and then the second, later on, the second horizontal vertical line gives you where the beam stops. So you should expect your vertex to be constrained inside that range. So that was nice to see that we are agreeing with what we expect to see, basically. So another key aspect of tactic is the detection of light protons. Is we detect protons, and then this is a nice plot showing a separation. This is a simulation plot showing the separation between the alphas up here, and then this shape here is basically the protons from the reaction. That's our interest. And you can see clearly that the protons will deposit very low amounts of energy inside the detection volume, and you can see it's like tens of keVs. So one thing we needed to verify inside tactic, although we have verified inside the test chamber that, well, we can detect 5.9 keV X-rays from an 955 source. Can we see those 5.9 keV X-rays inside tactic? Yes, we can, in the same gas mixture. So yes, that gave us confidence that we can indeed have low enough detection threshold in terms of energy to identify these protons. So yes, based on that, we had our very first successful cross-section measurement, 15 years in making, but we had it finally with tactic. So we measured the reaction cross-section of 23 sodium alpha P in inverse kinematics. And this, the blue data points are highlighted by this work. This was from our work, the recent work at TRIUMF. So they agree quite well with the predictions and the previous measurements as well. So the higher 3 points, I will come back to them. They were dominated by fusion evaporation reaction on the quench gas CO2, but fortunately, they're outside our energy range of interest. So key highlights from these measurements, from this particular measurement is the beam intensity that we used is 5.3 × 10⁶, which is high, and that's basically higher than the music measurement, the ANL measurement that was done, almost 2 to 3 orders of magnitude high. So that's that was our goal, to do the measurement at higher beam intensity by taking advantage of the cathode gauge. Also, please note that this run duration was only 3 hours. So in 3 hours, we could extract a reaction cross-section only because we could utilize high beam intensity. That tells you that, like, if you can go to high intensities, you don't need to run for longer, and that gives you specific advantage when you have very precious radioactive beam time. Also, another thing I want to note, due to lack of instrumentation, the geometrical efficiency of tactic for this particular run was quite low. It's 6.1, but still it was enough for us to do a good statistical evaluation at low energies for this reaction to extract the cross section. And this plot on the bottom plot shows you the angular range that was covered. So that around 20 to 60 degrees in the forward direction. So that's basically our forward angular range that we're looking at. We didn't look at the backward angle because the differential cross-section is lower for the backward angles. So once we have like more data, hopefully from the 2024 run, we can look at the backward protons as well. They should be completely background free. by background, I mean scattering background from the gas. So yes, so again, I highlighted this, that although the efficiency was quite low and we could only instrument one sector of tactic for the run, we are looking into full instrument tactic right now. So before we run next time, we should be able to increase our efficiency by order of magnitude almost. So that will be something that will give us like a very good definitely an advantage when we run. Yes, and also I would like to highlight again certain key points that like we measured at 3 orders of magnitude higher beam intensity almost compared to the music measurement that did the same measurement in 2026. We had a vertex energy resolution around 180 to 190 keV in the center of mass frame. Please note, we can go lower in vertex energy resolution by reducing our gas pressure. Tactic ran with the highest possible gas pressure, which is the worst condition for a vertex energy resolution. So this can be improved when we run with a lower gas pressure. We can go to 100 keV probably in the center of mass. That's pretty good. So the detection threshold, like you see, like I showed before, was quite low. It's like in the order of tens of kVs, even lower, because we could see the iron 55 source. Also, the cross-section measurements that we did agree with the previous measurements with like 5 to 10%. So we are in line with the previous measurements, the argon measurement, and also the TRIUMF measurement that was done with DUDA back in 2015. So another thing that I want to highlight here from this particular ID plot, the vertex, the energy, the y-axis, basically, the vertical axis signifies the energy loss in one path, the highest energy loss inside a track. So basically, that's the delta E for tactic, and then as a function of vertex position. So you can see as you go higher, lower in energy, higher in vertex position, you have better separation from the background. And here, in the beginning, you have like the fusion. Sorry, okay. So you're dominated by fusion evaporation on carbon and oxygen in the target. So it's really difficult to identify or to put a constraint on the reaction protons of interest. But that's good news for us. We actually get better at lower energies, which is what we are trying to do. Right? So yes, in order to summarize, so yes, the gas amplification stage, novel micro-RWELL and electronics, the DAC, all of them were modified during the period of 2019 and 2023. That is my PhD timeline. And the first cross-section measurement was performed using tactic, and the results do show a good agreement with the statistical model and the previous measurements as well, like I mentioned. So that's leading to this should lead to a commissioning paper. We are working on that and should be able to publish in 2025. And based on our successful studies with the sodium 22 stable beam, we just got recommended high priority radioactive beam time, and we're hoping to run tactic with radioactive beam in 2025 this year, basically a TRIUMF. So that was a very good result, leading from the sodium measurement that I talked about. So what's for the future? So we are planning to do a comprehensive study of the micro-RWELL. So we need to study the performance in detail. The optimization studies can be done in order to understand what pressures, what gas mixtures can be more useful or will be better for tactic. Also, like I mentioned before, we are currently looking into upgrading the DAC that will give us a full instrumentation of tactic, increasing the geometrical or the detection efficiency. In the future, we are also have plans to have like a silicon detector array around TACTIC, a flexible silicon detector array that will be take shape in a cylindrical shape, a barrel detector, think Alice or something like that. So to stop the protons completely. So now we don't stop the protons inside because they're light and they hit the radius of the surface of TACT or the boundaries of the detection volume. So silicon detectors will be able to stop the protons, will give us some more advantage in terms of particle identification. Also, the optimization and redesign of the micro-RWELL detectors can be done in the future. Better micro-RWELLs will allow us to go to higher rates in terms of beam intensity or the number of events we can detect. And also, it will give us advantages in terms of like the intrinsic properties of micro-RWELLs. There's like micro-RWELL development is constant and it's changing every day. So it's getting better as we speak. So already the micro-RWELLs that we incite TACTIC are backdated. So we have plans to update that in the future. Also, maybe a potential redesign of TACTIC to make it more versatile. TACTIC is really tiny. People have seen it. I'm sure a few people in the audience have seen TACTIC. So maybe we will look into a redesign that will focus on making like implementing other detector systems like silicon or maybe a neutron or gamma ray array in the future. So with that, I would like to thank you all for listening in, and a big thanks to my collaborators, all of them, and especially my supervisor, P Supervisor Allison, for pushing TACTIC and having faith and not losing faith even after 15 years, right? So we could have some nice results. And I'm quite sure that TACTIC will contribute to the nuclear physics community in general in the future. So with that, thank you. And I will take in questions if you have.